And now we're ready. It's time for the best content for today. Our guest speaker, Vasily Tsouvalas. Um, I will stop sharing right now. He's
Okay.
joining us from Eindhoven, the University of Technology, and has prepared a really cool talk about federated learning with noisy labels.
Can you see my screen?
Yeah, looks great.
Let me draw a laser pointer. Okay. Hi all, I'm Vasilis from Eindhoven University of Technology, and today I'll present you our joint work together with Aagib Saeed, Tanir Ozcelebi Nirvana Meratnia from also Eindhoven University, which was revolving around noisy labels in federated settings. So, starting on, I'll skip the introduction slide for federated learning. I assume that all of you are familiar with this. And I will basically just go directly into the major challenges that exist at the moment in federated learning. And I categorize those as four. So this is usually how it's been done. So the first one is the privacy guarantees, which basically, the reason why we started federated learning in the first place to take control of the data and to regulate the access. And this regulation of the access also affects who can actually see the data, who can label the data as well, as we'll see it later on. So the second thing is the fact that we're talking about distributed machine learning. So that means that we can have multiple devices with different computational resources, but they can also operate in different energy budgets as well. So you need to adapt your training procedures to mitigate different system heterogeneities that exist here. The third one, which is actually the one we will not be touching a lot today, is the communication restrictions that exist in federated settings. So as you communicate model updates from server to clients, this channel a lot of times is noisy and unstable, and sometimes also with very limited bandwidth, which means that communicating these updates can become challenging, and how often you can do that is also something that can challenge the training procedure. And the last point, which is the data heterogeneity. Yeah, so as I said, the data are distributed here and are closer to the user, which means that the data follows most of the time the profile of the users that operate the devices, and that makes the distributions between the different devices different, and also the training procedure can be much harder in these settings where you have non-IAD distributions. Um, so before moving on into our technique, I want to introduce the label noise first, and then the label noise in federated settings. So as you can imagine, what is label noise? So it's the fact that we misclassify label samples. So I posted here some of the popular data sets. You can see that even in these data sets that are basically have been iterated through multiple labelers, there still are examples here which are misclassified. And this phenomenon becoming even more dominant when you go into settings like ImageNet, where you have weakly supervised datasets, where you can have more than 100,000 samples that have label issues, as you can see here. And the list of datasets can be surprising. So I talked about MNIST, but also CIFAR has noisy samples. Audio set, so also audio datasets have noisy samples. So my point here is that real world data are, as I said in the beginning, in the title, are messy. So you need to also consider this when you are training your models. But And now, if we consider federated settings, so as what I showed before is datasets that exist in centralized locations have been labeled by annotators, multiple of them. And when you move to federated settings, you have to regulate access on the data. So yeah, oracles are labelers, and they are just humans, so they can make mistakes. But also, they're not any kind of humans. Most of the times, they're just the users that operate the devices, and this means that users have to annotate their data, and users most of the time might have lack of knowledge for a particular task because so this also creates inconsistencies in the standards when you label, because the users might be affected by the multiple things when they label the data, but they can also be biased based on their experience, or they can also be tired and just misclassified because they didn't spend enough time. And there is not a way here to use multiple labelers and do a majority vote on the actual correct sample to mitigate this noisy label. So the data, you should expect them to be extremely noisy. And we will see also in the end some data sets that some people that they try to do this in, and the outcome is that they actually a lot of noise in the federated data sets. So before moving on in our approach, I wanted to give an introduction on how this idea originated. So we started this by reading the paper in Confidence Learning by Curtis in 2021, I think, which was dealing with label noise directly by using the existing training model. So basically what they were doing is iterating through the model that they were training to do some statistic analysis based on the model outputs to find the noisy samples and do this procedure over again in order to create in the end eventually an even better model, which is also our goal. So they also have a library for this, but as you can see later on, there are some problems when you try to apply this confidence learning in federated settings directly. First of all, so this iteration process requires a lot of time, and in federated settings where you have devices that operate in energy budgets, this is not optimal. But this is not the only thing. The fact that these models are basically the client's users model, sometimes they are unable to capture specific noise patterns that exist in particular users. So applying just confidence learning directly on the federated settings by just estimating the noisy samples from the local model is not enough. And we also ran experiments when we had more concentrated noise. What I mean by that is that we had classes that are basically users were hard to distinguish. Imagine like a tiger and a jaguar. In these cases, CleanLab didn't perform that well. And you also need to keep in mind that when we move from centralized to federated settings, now the data most of the time become a non-IID, which means the initial model performance will be poorer than the one you had in centralized settings. So for the last 1.5 years, we were working on a framework to provide a solution to this. So we call this FEDELEN. So the main point of this was that we were trying to detect and correct noisy samples, but also wanted to take advantage of the multiple stages that are happening in federated settings, something that CleanLab was doing. So we try to basically mitigate label noise in different stages, initialization, training, and aggregation in particular. And we will present in the next slides the techniques for each of them. But we also provide with this framework per client noise estimation, and we provide the technique in cases devices operate under low compute powers. So solutions in cases where you cannot really run extensive computations. I'll start with the first one. The first technique we basically looked into was the near neighbor correction. So the process here was a three-step process, basically. So you were just extracting features on your local data using an off-the-cell pre-trained model. Usually those were self-supervised, so they could provide some features which are good for downstream tasks. And what you do next after you have these features, you apply, you are looking basically in the neighborhood of the samples in the feature space to find which are samples in this space is outliers. We use KNN for our experiments, and then basically all the misalignments between the estimated labels and the considered, the provided ones were considered noise. And in this way, you could do a majority vote and decide if this noisy sample should be flipped to another class. Some remarks about this process is that the features of the pre-trained model here act as a noise-free source. So this also means that the performance of this approach highly depends on the quality of the features. However, we've seen nowadays that there are more and more like foundation models and this kind of models that could actually provide very good features. So we don't believe that this is actually a big issue, finding good quality features. But also, you need to notice that we run this process only once, and you can run it before even the initialization phase, basically. So before the training process starts, to basically clean your data and then train with a clean, corrected data set. This process basically is similar to the confidence learning, but instead of the own model, we use the off-the-cell pre-trained model. And I provide here a visual intuition on what I described previously. So this is I think, the CFAR10. And we just create we plotted the feature space before applying the nearest neighbor correction process. So as you can see, there are regions in the map, like here or here, where you can see that some samples are allocated in a cluster where they seem that they shouldn't be there. So by doing a majority vote to decide which samples are actually the correct one, which label is actually the correct one for the samples, you can basically mitigate a lot of noise in your dataset. And as you can see, the next figure now, all these samples have been categorized to belong to these clusters. Of course, there are cases where samples are just outliers and they belong to the class, but this we've seen also in the experiments that those cases are the minority. But moving on to the next technique, so there's cases where actually devices cannot run these kind of models, these pre-trained large models to begin with. So for this case, we took into a different approach, and we considered to estimate the label noise of clients based on the energy score of the outputs of the locally trained model. And so in case you're not familiar, the energy score is basically what it tries to do is check the ranking of the embeddings. And it is shown that also in most of the cases, so when the samples are trained, they usually being compressed in a lower feature dimensionality space, which means the ranking is then decreased. So the process here on what we are doing is we basically compute these energy scores on the logic, so on the outputs of the model for the model we receive initially to the local device. So we run this inference based on the data on the global model we receive in each round, in one round, and we get the energy score for the data set, for all the data, and then we train the local model and we run exactly the same process on the trained model. So we have basically two sets of scores, and using the initially received model prior to training, we compute the energy threshold basically to determine which samples should be noisy. And for this, we use the 75th percentile. Of course, there can be other statistic methods you can use, but we saw that also in the paper that this was good enough and didn't require a lot of computation. And then by then, you just categorize the samples based on the score of the locally trained model outputs, energy score outputs, if they belong to the noisy set or the clean set. And you can easily estimate the label noise on the client. And what we do basically with that is we basically send this noisy level in the server side, and we take it into account in the aggregation. So this box here is representing basically the Fed averaging, and we introduce this term here to basically correct or mitigate the noise level on the client. So noisy clients have less effect on the global model, making the whole process much more robust to noise. So again, a visualization of this is what I had here is basically I have plotted the energy score in different bins. So here is the frequency that the actual score is occurring. And I have basically colored differently the noisy and the clean samples on one client. And you can clearly see that the energy score have a clear separation because basically all the noisy samples after a few rounds of training basically do not fit the model well. So in the beginning, the models usually, this also have been researched, usually tend to fit in the most easy samples before moving on to the hard examples. And label noise can be considered as a hard example because you have a lot of samples in one class, but then you have some samples that don't belong here. So in the beginning of the training, like in the first few rounds, usually the model learns the clean samples, and then that's why also the energy score is higher in these cases. Some remarks here. So here the difference with the previous thing was that the clean clients, the clients that don't actually have a lot of noise, are the source of the noise-free source that you use to accurately estimate this threshold. And the sources are computed only once. So what we did was basically measure these scores across the few rounds, and we decided that after a few rounds to compute the score in that particular round in the client side and decide the noise level. So this process happens only once in the client. And after you have the noise level estimation, you just continue training as usual. So you don't need to reconsider this. You just aggregate the models based on the noise estimation level. Of course, over time, in real settings, you can also apply this technique periodically to correct the noise level. And we saw that the effectiveness actually of this technique, the noise-aware Fed averaging, depends really on the separation between the clean and the noisy clients. So as you can see here. We also have a lot of experiments in the paper showing that if you start adding noise to all the clients, then this process starts to become less robust. But you have even a few clean clients, that this process can be much more stable. I said a few rounds. So as I said, we ran some experiments. So what you see here is basically the training process without applying any technique to mitigate noise. But we were basically, what we were doing was computing the AUC score. basically the how well it detects the noisy samples on the clients based on different techniques. So you use the confidence learning paper statistics that they were run in the existing model. We only run directly the softmax output of the model, but we also measured the energy score that we were working on. So you can see here that after a few rounds, you can easily understand the noise. But after that time, it doesn't improve. And actually, if you train longer, as I said, it starts to go down again because the model starts to fit also in the noisy samples. So we actually just ran some experiments, initial experiment in the paper to find that around 25th round, you can detect a good amount of noisy samples. So you can improve much the performance of the model by just incorporating this noise level estimation of the clients. And as you can imagine, this computing of the energy score is quite inexpensive. It was also visible here. It's just a log exponent summarization of the logic of the outputs. So it can run in most edge devices without affecting much the computational resources, which is ideal for low compute power devices. And we also proposed a last approach, which was more complementary to the first one. And the idea here was, instead of doing this KNN on the embeddings, directly utilize the features during training. Of course, this technique requires more computational resources, but here you mitigate any kind of noise that can be introduced by the labels of the labeling of the KNN clustering, because you utilize directly the noise-free embeddings. So basically, as I said, what you do here is affect the local training on the client. So you have the embeddings, and what you try to do is try to minimize the divergence between the of the cell model, which is acting as a teacher, and the student model, which is trained on device. And by using the KD divergence here, you basically minimize the difference between these models, effectively trying to mimic the performance of the teacher model. And you only adapt here the loss function. So the rest of the training process is not really affected. So I'll move on to some interesting results from this. So we ran some experiments across different data sets, but also across different architectures with 30 clients. But before moving on to the results, I want to specify a bit of the noise injection process. So in the paper, we consider the noise is not class dependent. So basically, you were creating a noise profile for each client based on the amount of noise you want the client to has, and how much concentrated the noise is in particular classes, which we name noise sparsity, similar to what they did in the confidence learning paper. So what noise sparsity actually tells us is that the higher amount of this value, the less classes are affected by noise, but the more noisy these classes become. With the extreme case of noise sparsity equal to 1, meaning that only 2 classes are basically noisy, and basically what happens then is you flip samples between the 2 classes. And we introduced the label noise to 70% of the clients. In the experiments that I'm showing here, in the paper we ran also with different kind of amount of noisy clients, but I omitted this since we are more interested in the approaches themselves and not the details of the results. So I have some results here. So I go through the baselines once to understand. So supervised, it's basically fed averaging. LS stands for label smoothing. So basically, we try to apply label smoothing in the loss term by directional and temporal loss function is basically another loss term that can mitigate loss, minimize the effect of noisy samples by basically trying to separate the noisy from the clean samples. And CL stands for confidence learning. And we also incorporated another technique, FedCore, which basically tries to learn a profile of noise for its client using a Gaussian mixture of distributions. So we ran some experiments. First thing you can notice here is if you compare the supervised settings with most of the techniques, you can see, so for example, for the nearest neighbor correction, you can see that especially in high level of noise, so we are talking about 70% of noise with a lot of concentration, you can see that the performance is actually improving a lot just by introducing this even in the initialization phase by just correcting the labels. And if you compare it with the best baseline from the ones we had, FedCore, which was also introducing multiple stages of training in order to mitigate noise. So it was, I think, it was using basically the first stage was to separate clean and noisy clients, and then fine tune on the clean clients, create pseudo labels for the noisy clients, and then train for the clients. So the convergence of the model was quite slow. So if you compare this with FedCore, you can see that the performance is improving significantly. And actually, there are cases, and this is what I want to point here, that when you have high concentration of noise, that actually the NNC process doesn't work that well. And I specifically highlight that to show that this is actually why AKD can make a difference here. And I will explain also why this is happening. So imagine if we go back to the case of the intuition of the NNC, you can see that imagine that you only have two classes that are flipping, let's say the blue, the orange, and the pink. So if those classes basically flipping in a high concentration and high level, it means that there will be a lot of orange points here, which means the majority rule here will just make the noise even higher, because it will see that there is a cluster of orange here, increasing the noise further. And this is why AKD here can be particularly useful, because here you don't actually use this KNN labeling, you directly use the beddings to train your model, and you can mitigate this effect and have a significant boost in the performance. And last, about the noise-aware fed averaging, although it doesn't perform the best out of the three approaches, considering that the computational resources it requires is very, very low, it can mitigate a lot of noise. In most of the cases, it's actually quite stable, even in high levels of noise, which was surprising even to us that it worked that well. So as I said, we ran more experiments in more data sets, which they were following mainly the same pattern, which was that the NNC was basically outperforming most of the data set, most of the noise settings, with AKD being especially useful in high concentration of noise, and noise-aware averaging being a bit lower in performance, but still producing quite good results without requiring a lot of computational resources. So I meted a lot of experiments. You can go to the paper, but I keep one which I believe it's the most important for real-time usage. And what we did here, so there were a paper, I think, in 2022, where they actually uh, hired people to classify samples, different users, in for CFAR 10 and CFAR 100. So they asked three different users to classify. They asked different users to classify this dataset, and they saw that there is around 40% of noise in the classification process. And this is why I said federated learning the data in federated settings can be especially noisy, because even in seemingly easy classes to classify, just 10 classes, you have significant amount of noise. I think for CFAN 100 was even more. And what we did was basically run all the baselines directly here. So we kept different, basically, we split the data based on the profile of the user. So we separated the data sets of one that are the data that were allocated to one labeler, to one device, to simulate a realistic scenario. And as you can see, confidence learning, especially in CFAR 100, lags a lot behind, but there are a lot of gains by incorporating just the noise-aware fed averaging. You can improve by in CFAR 100 by 6 points just by adding this noise estimation. And the interesting thing here is that although because of the difficulty of the task in CFAR 100, embeddings, the KNN algorithm produced a lower result than AKD. So assigning directly the embeddings can help much more, although it will have a much higher compute. And in easier tasks, you can just incorporate this noise nearest neighbor correction in the initialization phase and perform much better in your dataset. So I wanted to summarize with basically this slide and the next one. So what we developed here was different approaches to deal with label noise in federated settings, approaches that targeting different kind of devices. As you can see here, depending on the compute resources, the energy budget, or even the storage and the memory capabilities of the device, you can try to select the appropriate one for your use case to mitigate the noise in different stages of the training process. And some concluding marks is that label noise in federated settings is occurring naturally, and you can actually not control it that easily. And it is also proven by the real-time use case that I showed. But also our framework tries to mitigate label noise by incorporating techniques in different settings where NNC can actually provide a label correction and its performance is stable in most settings. Noise-aware fed averaging could run in resource-constrained devices and try to mitigate the noise by aggregating the noisy clients' weights by adjusting the noisy client weights in the aggregation process. And AKD can be especially useful, I believe, in cross-silo federated learning, where you have participants that have large computational abilities, but they have noise in their data, either because of the knowledge expertise missing, or because they perform some weakly supervised labeling on their data. And with that, I want to close the presentation. Thank you very much. You can find the links to either the code or the paper in the QRs.
Great talk. Thank you so much. That was really nice. Very interesting. Very nice visualization as well. Great.
Yeah, thank you.
Very good for following along. And we already have the first question.
Okay.
It's from Yang Gao. I will just read it out to you. Is it necessary to use self-supervised model to do noise cleanup? Can you use pre-trained supervised model?
You could actually use them. Usually, the fact that the self-supervised models are trained in larger data sets are the fact why we also focus more on that. But there is no actual limitation. You just need good enough embeddings that can capture the downstream task. And this is something that you can play with. And actually, recently, what we were trying to do instead of using one model to compute the embeddings, use a mixture of models to try to improve further the embedding space and do a majority vote over the embedding to actually find where these labels should be classified.
All right, nice. Thank you.
Well, and thanks for the great talk. I have a quick question. Basically, if I apply your methods, the FedLN, to a clean data set, I'm just wondering, will this cause huge computation overheads because it's a clean data set without or with minimal number of wrong labels?
Yes, so actually we tried that. I saw that in most cases, when you use the pre-trained models, you introduce a small percentage of noise. Usually was based on the task difficulty, 3 to 10%. With noise-aware fed averaging, although it really depends on when you actually introduce that. So my belief is that if you introduce this energy score calculation very late in the training process, the percentage of noise estimation will be much smaller. But if you do it very early in the training, it might produce undesirable effect, I believe.
Thanks for the explanation.
Yeah, thanks for your great talk and thanks for the answer. I just have a follow-up question
Yep.
at the last one. So you mentioned, yeah, so we can use a large, for example, the self-supervised model to do the pre-training. So I'm just wondering if the pre-training on the different data sets or on the same in practice.
No, the pre-training was happening in completely different data set. Usually, as I said, self-supervised, so without even labels in the server side. So, for example, what we used in our experiment was just using the clip model to extract the embeddings. So nothing to do with the data sets, the downstream tasks at hand. If the server, of course, had data that captures similarities to the tasks that the users are training on, of course, the results will be just increasing further, I believe. But usually that's not the case in federated settings.
Okay, I see. Thank you.
I actually think I have one last slide I forgot to present. So, yeah, this is, I guess, very familiar. This is the Fed averaging in flower. So we are using actually flower as well. We are using that for the last, I think, 3 years. So thank you a lot for the framework. Actually, from the beginning of the PhD. So the noise-aware Fed averaging is just a matter of adding this, as I said, clean examples. In the aggregation process. So it's very easy add-on, I believe. And you can estimate the noise however you want. We use energy score, but of course, softman score can produce also desirable effects. So it doesn't have to be something more sophisticated to mitigate the noise. And yeah, I wanted to also thank a lot about the framework. Helped a lot with simulations in the PhD, especially the last year with updating the simulation framework.
And that's very great to hear. Thank you so much for using Flower and joining the community. So
Yeah.
thank you as well. I received also a question here. And wait, no, I swiped away. Oh yeah. Are there any specific domains or applications where you believe FET and LN framework will be especially beneficial? So I guess this is a question for maybe real life use cases.
Yeah, so we ran some experiments with PathMNIST. So in case you're not familiar with this is a medical data set for the MedNIST data set. So it does try to fight pathological diseases in the lungs. And I believe this is one of the domains that can especially be useful, mainly because the knowledge and expertise in these particular domains is lacking for most of the users. Of course, nobody can take the like a picture of their lungs to have in the local data, but in a cross-silo settings, you can have hospitals where they have this data, they just don't have the medical experts to annotate them. And this can be especially useful, I believe. So medical domain is one domain that I really think this can be especially useful.
Great, yeah, sounds good. And I have another question here. Were there any particular challenges you faced while developing FET-LN framework next to the good quality features?
Yes. So initially, we tried to look into augmentation to mitigate the label noise. So that was a lot of problems came up, and we actually couldn't use it. So um, also the one of the biggest challenges we had was to find how to detect the noises data from the directly from the model effectively, uh, because confident learning was using a iterative method, as I said, that was running the data through the model multiple times to detect the noisy samples from the scores. But we couldn't use something like this because it would computationally expensive. So we were looking at a lot of uh, uh, score-based techniques to detect this, and then we were trying a lot of statistical methods in order to see which one works the best without introducing a lot of computation overhead and derived to the 75th percentile.
Cool. Thank you for the explanations.
Yeah.
I'm just going to check again the different channels. We don't want to miss any questions. Yeah, I think we got them all.
Okay.
Great. So then, thank you very much again for your amazing talk.
Yeah.
For everybody out there, we'll be uploading the video hopefully as soon as possible. Yeah, thank you so much.
Yeah. Thank you
all
for
the
the
links
invitation.
already. Feel free to check out the code and the paper and GitHub as well.